We can also define refractive index in terms of velocity of light. The very first equation for refractive index that we got from Snell's law was mu is equal to sine I upon sine R. This is a new equation that we are getting today. It is absolute refractive index. Again, mu is equal to velocity or speed of light in vacuum upon velocity of light in a given optical medium. We use the word absolute to show that the first medium is air or vacuum. In case the first medium is not air, we come to the second equation. When light travels in two different media, A and B, then we write mu of B with respect to A. Remember, first medium comes at the superscript, that is A, and the second medium is written as a subscript, that is B. So, and refractive index is always for the second medium. So, refractive index of medium B with respect to A is equal to speed of light in medium A upon speed of light in medium B. Here we come to explanation of an important statement. Explain the statement that refractive index of glass is 1.5, or explain the statement that refractive index of water is 1.33. Now the first statement, if I talk about glass, refractive index of glass is 1.5. We are saying that with respect to air, this value is with respect to air, which is fixed. So it means that when the ray of light is traveling from air to glass, its velocity or speed decreases by 1.5 times. And if I talk about water, then when the ray of light is traveling from air to water, its speed decreases by 1.33 times. That is how we explain this statement. Also, we should notice that refractive index is a pure number. It is just written as 1.5 or 1.33 without any unit. That is because refractive index is a pure ratio. It is either velocity of light in vacuum upon velocity of light in given medium, or it is sin I upon sin R. In both the cases, both the units of numerator and denominator get cancelled off, and hence refractive index is a pure ratio. It does not have any unit. Lateral displacement. If you look into the diagram given here, we are still talking about refraction of light through a glass slab. If there was no glass slab placed, the ray of light would have gone straight along this path. In the absence of glass slab, this was the original path of the incident ray. But since there is a glass slab placed, the ray of light has bended, and now it is following another path, that is at the first interface it is bending towards the normal. At the second interface it is bending away from them. So we can clearly observe that the ray of light has slightly shifted from its original path. The ray shown in the pink is the original path of the incident ray. The ray that is shown in blue that is coming out of the glass slab is known as emergent ray. And you can clearly see how the ray of light is shifted just because we placed a glass slab in its path. This shift in the path of light, that is, I'm talking about this distance. This shift in the path of light from its original position is known as lateral shift, or it is also known as lateral displacement. Remember, the ray of light has shifted from its original path just because we put a denser medium in its way. Coming to the definition of lateral displacement. The perpendicular shift in the path of the incident ray emerging out from an optical slab is called lateral displacement or lateral shift. In the figure, RS is called lateral displacement. You can see clearly RS is known as the lateral shift or lateral displacement. Now, lateral displacement of this ray of light depends upon four important factors. Number one, It is directly proportional to the thickness of the glass slab. That means if I'm using a thicker glass slab, the lateral shift of the ray of light will be more. It will shift away more because obviously it will bend more. Number two, it is directly proportional to the refractive index of the material. In other words, density of the material. More the density, more will be the bending, more will be the lateral shift. Third, it is directly proportional to the angle of incidence. The moment we change this angle of incidence, we can see here, the moment I change the angle of incidence, obviously the path of the ray will change, and if I increase the angle of incidence, the lateral shift will also increase. And the fourth one, the only factor which is inversely proportional, lateral shift is inversely proportional to the wavelength of light. Again the same thing. Lateral shift of red color will be less because its wavelength is more, while lateral shift of violet color will be more because its wavelength is less. That was all about lateral displacement or lateral shift. We are supposed to remember the four factors on which lateral shift depends. Again, three factors directly proportional and one factor inversely proportional. Next, we come to principle of reversibility. Principle of reversibility is a special case. The statement says if a ray of light travels from medium A to medium B along a certain path, it will follow exactly the same path while traveling from medium B to medium A. So if we look into this diagram given on the left hand side, we can see that the ray of light is traveling from medium A, that is redder medium, to medium B, that is denser medium. So as soon as it strikes the interface, since it is going from redder medium to denser medium, it will bend towards the normal and it will follow this path. Now if we place a mirror in its path exactly at 90 degrees, we know that the function of the mirror is to reflect light. Now since there is a mirror placed, the ray of light will be reflected. Now the ray of light will travel backwards from medium B to medium A following the same path. It is going along the same way through which it came. This principle is known as principle of reversibility. But the condition is the plane mirror should be placed at an angle of 90 degrees with the ray of light. So I am reading the statement again. If a ray of light travels from medium A to medium B along a certain path, it will follow exactly the same path while traveling from medium B to medium A. Does not change its path, provided the plane mirror is placed in the second medium exactly at an angle of 90 degrees. This principle is known as principle of reversibility. Principle of reversibility can also be explained with the help of another statement, a second alternative statement for principle of reversibility, which says that the refractive index of medium B with respect to medium A is equal to the reciprocal of refractive index of medium A with respect to medium B. So if you look into this equation that is given on the right hand side, this equation gives us refractive index of B with respect to A. And if I want to find out refractive index of A with respect to B, that is, if I just want to change the media, the first medium becomes the second medium becomes the first medium, I just have to take the reciprocal of that number. For example, if we go back to the example that I had given last time, that refractive index of glass is 1.5. Now, when I say refractive index of glass is 1.5, that is with respect to air. The other way around. If I want to find out refractive index of air with respect to glass, we shall simply do 1 upon 1.5. That will give me the refractive index of air with respect to glass. That is the meaning of principle of reversibility. The next topic that we are going to talk about is apparent depth and real depth. Now, when we talk about depth, remember we are looking from the top of the surface. There is a huge difference between depth and height. Height is always measured from the ground level towards upwards, while depth is measured from the free surface upwards towards ground. Real depth. The actual depth at which the object is situated in a medium is known as its real depth. Apparent depth. The depth at which the image of the object is formed when viewed from the top surface is known as its apparent depth. And we come to the third equation of refractive index here. Refractive index equal to real depth upon apparent depth. To get a better idea about real depth and apparent depth, we consider two optical phenomena. When we place a pencil or a stick inside water, the stick or a pencil appears to be bent, short, and raised in water. That is obviously because of refraction of light when the ray of light is traveling from water to air and it is entering our eyes. So this position, the lowermost position which is shown as A, is the real depth of the pencil inside water, while the position shown as A1 is the apparent depth of that pencil inside water. So the difference between real depth and apparent depth is real depth is the actual depth, while apparent depth is the depth that we are able to observe. It is the image that we are able to observe just because of refraction of light taking place. Similarly, in the case of a coin, the coin is actually placed at point O. O is given for the object. This is the object, that is a coin which is placed deep inside water at the bottom of the beaker. But since refraction of light is taking place, we are able to observe the image of the coin at point I. This I is the apparent position or apparent depth of the coin. So there are few similar phenomena that we can explain based on refraction of light. First one, a pencil appears to be bent, short and raised in water. Second one, a coin appears to be raised and enlarged in a beaker filled with water. Similarly, a stamp appears to be raised and enlarged under a paperweight, and a fish appears to be slightly raised under water. Remember, anything that is put inside water will always appear to be slightly raised and slightly bigger. So when we draw the ray diagrams, we should be careful that A is the actual depth or the real depth of the pencil. Two rays of light are emerging out from the tip of the pencil. When this ray goes when both these rays go from water to air, that is, they are going from denser medium to rarer medium, they will bend away from the normal. So we are going to draw two normals for both the rays. And now these rays are bending away from the normal and they are entering into the eye. So when our eye retraces the path backwards, we shall observe that we are able to observe the path of the ray that is coming from point A1. It is not actually coming from A1, but our eye retraces the path backward, and instead of A, that is the real depth, we are able to see A1, that is the new image which is at the apparent depth. So we can see that the pencil appears to be slightly raised. Same in the case with coin. Two rays of light are coming out of this coin, and when they are traveling from water to air, they are going to bend away from the normal and enter into the eye. If our eye retraces the path backwards, we can see that instead of O, we can see only the apparent image of the coin that is at I. And we can find out the refractive index of the second medium by using the equation refractive index is equal to real depth upon apparent depth whenever we know the value of real depth and apparent depth for a particular experiment.